Okay.
Okay, so now we're going to look at what happens when we have a magnetic flux density vector which changes with respect to time and what's going to happen based on that. So if you see here, we have a magnetic flux density vector V, which is a function of time, okay? And you can see that it's pointed here at the board. Now, if you look at this statement here that says, if B of t is increasing with respect to time, I induced will be in the blank direction, okay? And I'll explain what the law is that says that, but basically, the law is Lenz's law. So Lenz's law states that the induced current will produce a flux which opposes the change in flux, okay? So this right here is what we call Lenz's law. Right? So this states that the induced current, right? So we're going to induce a current from the change in magnetic field here, and that induced current is going to produce magnetic flux which opposes the change in flux. So think about this. If we have B of t here and it's increasing with respect to time, that means that this field in this direction is getting stronger as time goes on. So we want to oppose the change, right? So we want to oppose the increase. So we have to think, which direction would current have to flow so that it opposes the increase in flux? Well, if flux is increasing from the board coming outwards in this direction, using the right-hand rule, we would see that we need a current which flows in the clockwise direction, and that would produce a flux going into the board and change oppose the change in flux, okay? So this would be in the clockwise direction, right? The clockwise direction, I induce, would produce its own flux, which would point into the board and oppose the change in flux. So that's called Lenz's law, okay? All right, now what if we had this ammeter here and we removed this and just had an open circuit? So basically, we would have something that looks like this. We just have an open circuit right here, okay? And we still have this same field, okay? And it's pointing from the board outwards, okay? And let's say it's increasing with respect to time. Now, we're not going to induce a current here because we don't have a closed path. There's no closed path for current to flow, but what we will do is we will induce an electric potential, right? So EMF. So we will induce an electric potential, V EMF, like that. And we will put the positive polarity such that it would induce the current if it was a closed circuit, which would oppose the change in flux. So if there's a higher potential here than there is here, current would flow in this clockwise direction and produce a flux which would oppose the change in flux. So this leads us to Faraday's law. Now remember, we're considering dynamics here. This is no longer statics. So if we look at Faraday's law, the simplest way to do this, if we have multiple loops of conductor, the EMF, the induced voltage, would be negative d lambda dt. Recall that lambda is what we refer to as flux linkage, which is just the magnetic flux times the amount of loops that it links. So from this right here, we see that we have a dynamic version of Faraday's law, right? So this is time dependent, right? If there is no change with respect to time, this is going to be equal to 0, right? So this is different than in the static case, okay? So how can we write this in terms of magnetic fields? Well, we know that flux linkage is basically going to be the double integral of the magnetic flux density. So we can say that this is equal to negative d dt, double integral of magnetic flux density. This should be a flux integral. Erase that there. There should be a flux interval, so we'll have it S there. Okay? So you can see now that we can calculate the induced voltage given that we only have the magnetic field. And you can see here that we have to have change in the magnetic flux in order for this to work. All right, otherwise we'll get 0. And that's what we had before. Okay, so one thing to notice here is we have this negative sign. All that negative sign is doing is it's reflecting Lenz's law that says that the current which will be induced will produce a flux that opposes the change of flux, right? So a part that students often make a mistake is with this negative sign and end up having a negative voltage. You just have to remember that there has to be a positive potential, right? A positive potential difference to have a current which would flow in that direction to oppose this change. So just be careful and not get tripped up with that negative sign. That negative sign is just reflecting Lenz's law. And sometimes we can actually omit this negative sign if we just understand that the positive polarity will be built up in that way. Okay, so now if we take this a little further, let's go back and let's remember in the case of statics, we had this. When we sum all the EMF up around the loop, it's equal to 0, and that's the static case. However, in the dynamic case, right, which we're studying now, that's not going to be equal to 0, right? So in the dynamic case, so I'll just put in parentheses here, static. In the dynamic case, when we sum all of E dot dl up, we're going to get the induced voltage. Okay? So something that you should see here that's interesting is we have an equation for EMF here. We have an equation for EMF here. We can set those two equations equal to each other. Setting them equal to each other, we can do a derivation, and we can get to the point form of Faraday's law. But first, let me write the integral form of Faraday's law by setting these two equal to each other. So it's going to say the circulation integral of E for a closed path is equal to negative the rate of change with respect to time of the magnetic flux. Okay? So this is the integral form of Faraday's law. Okay? So the integral form of Faraday's law there. So this equation holds true no matter what, whether we're talking about the dynamic case or we're talking about the static case. And how does it? Well, if we're talking about the static case, that means that all time derivatives are equal to 0, right? So in the static case, if time derivatives are equal to 0, that means this term on the right is equal to 0, and we basically have KVL at that point, right? Kirchhoff's voltage law. If we have time derivatives that aren't equal to 0, well, this equation still holds true for the dynamic case. So either way, we can still use that for either case. Okay, so this is the best representation of Faraday's law. Okay, so this is the integral form. How can we get to the point form? Well, we should notice on the left that we have a closed path integral around, and that's a line integral, right? So we should know that we can relate this to the curl of E using Stokes' theorem. Okay? So using Stokes' theorem, we can say that this is equal to the flux integral of the curl of E. Okay? And this has to be equal to this, so this also has to be equal to this. Right? So we would say negative d dt B dot ds. Okay. So now we should note that B depends on two things. It depends on time and it depends on space, right? But this is a time derivative here, so when I take this to the next line, I'm going to actually use a partial derivative to make sure that we understand that we're only talking about the rate of change of time and not space here for this, okay? So from this point, we can see that we have the flux integral of curl of E. We could bring this time derivative inside because, like I said, this is a flux integral, which is spatially dependent, and this is time dependent, so we can be put in or out in either case. And from here, we can say that the curl of E is equal to negative partial derivative of B with respect to time. And this right here is the point form of Faraday's law. Okay? So now that gives us another one of Maxwell's equations. We have the integral form of Faraday's law, and we have the point form of Faraday's law. Okay? So this gives us one of Maxwell's equations, but in the dynamic case.